Hey guys, welcome to section 3 of my course on quantum mechanics. And in this video, we're going to start learning about function spaces, another way to generalize Hilbert spaces. But first I want to start with a brief review of some of the things that we learned in section 2 that will be very, very important in this video. So to start with, we learned that I'm going to rewrite that. We can write a state vector for a quantum particle, right? And we can write this in a superposition, right? Psi is C1, phi1, right? Where phi1 is, for example, the state with, remember we learned about observables, phi1 has big Q, the observable, equal to some value Q1, right? Etc. We can generalize this, and I'll first start. This is C1 phi1 plus C2 phi2 plus dot dot dot, which is, right, this is the same thing we're writing as a sum over all possible values of j of C sub j times phi sub j, right? For all possible values of j, so we can have one state, two states, three, four, however many, up to, an infinite number. And phi sub j has some observable q equal to little q sub j, right? Um, we also know that probability of the particle having big Q equal, if it's in the state, probability of big Q being equal to little q sub j is that coefficient C sub j norm squared, right? We also learned that C sub j is the inner product of phi sub j and psi. And again, we have that proof in, I think, multiple videos. Which then, using these two together, we can see that the probability of Q being little q sub j is equal to the norm squared of this inner product. And this is all given that the basis, right? Phi inner product with phi n this is an orthonormal basis, which means this is delta mn, this is the Kronecker delta, which we know from a few videos ago in section 2. This is 1 if m equals n, 0 if m does not equal n, right? So the inner product of, say, phi1 and phi1 is 1, but phi1 and phi2 is 0. Okay, so these are just the important things to remember. Hopefully you have that down. Hopefully this makes sense. This should just be a quick refresher on these equations. Okay, I'm going to erase this, and we're going to start with our section 3 stuff. So now, again, I'm going to say that the state phi sub q has some observable big Q equals to little q, right? But I'm not using the counting indices anymore, and I'm gonna show you why. I'm gonna tell you why in 1 second. So I want you to go through this thought experiment, or if you have say a die, right? Like a six-sided die. You may want to actually get that out to sort of see what I'm talking about, right? So if we're rolling a die, well, there's two things that we can actually see from this, right? And one, the first thing is when you roll it, you can measure it's either a 1, 2, 3, 4, 5, or 6, right? That's one property. That's sort of in a way quantized, right? Because you have 6 discrete possibilities. Well, when you roll it, there's another thing, right? it can actually land in a physical location, right? So say I've got, some playing a board game and I've got a die, right? I can't really draw in 3 dimensions, still going to try, right? We've got a die that we're going to be rolling, right? And we roll it, right? It lands in one spot. It lands on one of its faces, but it also lands in some spot here. Now, where it lands is not a quantized property, right? It can land here, but it can also land an infinitesimal distance next to it, right? Just a tiny little distance next to it. It can land, say there's a good probability it lands here, good, slightly less here, right? Hopefully, again, I'm going to erase this, but hopefully that makes sense, that there's another property about the die, where it lands, its physical position that it lands in, that is not quantized. It is continuous, right? It can't just land here, 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 or here, right? It can land here. It can land right next to it. It can right? There's a continuous number of possibilities of where the die can land, and quantum particles work just like that, actually with position as well. In all cases at least that I'm aware of, there's no time. There are places, you can say, oh, this electron can't be here, right? Just like if the die you had some kind of hill, right? Like, or some kind of peak on your board game, well, the die can't land right at the top of that, right? Um, but in terms of like electrons or other quantum particles, there's not, a single quantized amount of locations it can land, right? There may be probability, right? And just like with the die, there's a probability it's going to land sort of, right around where you roll it, but there's always a little bit of probability that it can roll away. You're not certain. You can't say, oh, for sure, right? Unless you just set it down. If you're really throwing the die, you can't say for sure it's going to land in this one spot, because it could land, an infinite, like, this tiny, tiny little distance right to the right of it or to the left of it, or, you know, in any direction, right? So it's the same thing with a quantum particle, that you can't really say, you can't quantize an electron's position. And quantum particles have a similar property to that die, right? Where there are multiple different properties. One of them, and some of them may be quantized, and some of them are not quantized. So we need to develop a quantum theory involving this probability, but for things that are not quantized. And if you look back, say, to the double slit experiment, right? You remember there was, the probability distribution looked something like this, right? Right? When we did that double slit experiment, we had, the two slits. It's not drawn exactly where the slit should be, right? But you set that those particles through, and it hits the screen, and it wasn't, a single peak right here, right? We'll actually talk about those kind of single peak distributions, and you'll see mathematically that they actually don't make any sense. But we'll see that in a little bit. Uh, in a few videos, actually. We're not going to explain that all this video. But um, but there was a continuous, right? It was most likely to be right here, right? But there was still a pretty good probability it would be right here, right here, right here, right? Again, there were continuous number of possibilities. The other thing, and first of all, right now, I'll go and write this down, and then we'll get to that next point. So we can write psi is a superposition of all the different states, right? Right, where we're adding up CQ times VQ, right? That's what our superposition is. We're adding them up, but we can't just add them up with, the sigma, right? Because that requires, didn't mean to do that. That requires a finite amount of states, right? Or not but it requires it to not be continuous. There's a first state, a second state, a third state, a fourth state. Well, in terms of like the position of that die, there's no discrete states. It's continuous. There's no way to discretely add them up. You need to add them up continuously. And possibly, you're seeing where I'm going with this, we have developed in section 0, or you're familiar with this from a calculus course, a way to sum up a continuous number of values, right? Or continuous values, and that's an integral, right? So when we're doing this superposition, we've actually got to use an integral, and we're going to integrate from negative infinity to infinity, right? And then dq, right? And the reason we've got this negative infinity to infinity thing right here, right, is this is integrating, it's adding up over all possible values of q, right? If you just ask yourself, what are the possible values of q? It could be momentum, it could be position, it could be anything, right? It can be, well, it's got to be somewhere between negative infinity to infinity. There's nothing else it could possibly be, right? So when we're adding from negative infinity to infinity, that's just the same way of writing, right, for the discrete case, writing a sum over j. That just means over all possible values of j, right? Here, we're adding up from negative infinity to infinity. That encompasses all possible values of q, right? So now, here lies the other problem, right? Because we've had this probability postulate, right? So in the discrete case, we would say that CQ norm squared is the probability of the observable being q. This means big Q equals little q, right? But I'll just write this: probability of little q is the norm squared of the coefficient. But for a continuous variable, this actually doesn't make sense, right? Because say the distribution for like rolling the die looks something like this, right? Where it's most likely here, but there's probability there's not one spot it can be. Well, if there's a certain probability it's here, think about the spot right infinitesimally close to it, right here, right? Well, there's going to be a very similar probability, right? So if this is like a 1% probability, well, then the spot infinitesimally close to it is another, 1%, and then 1%er may even say this is higher, like a, 20% probability. Well, then right next to it would be like 19.99. And then as you're adding all of them up, right, because you're adding up the probabilities for an infinite number of values, they can't have a finite probability. There can't be a finite probability here and a finite probability in infinitesimal distance to the right of it, and then a finite probability in infinitesimal to the distance to the right of that, and then the same thing, finite probability in infinitesimal distance to the right of that. We'd be adding up an infinite number of finite probabilities, right? Or non-infinitesimal probabilities. That doesn't work, right? You can't define, and it wouldn't make sense to define a certain probability that it's right here, right? That if you're rolling your die, that it lands right here. That wouldn't make a lot of sense, right? Because then, you're essentially saying it's got to be right there, right? So that probability doesn't account for the little probability that it gets slightly 0.000001 millimeters to the right of it, right? That wouldn't make sense. What would make sense is saying there's a probability that it lands between that it lands somewhere between this point and this point. Hopefully that makes sense to you, right? That saying a probability it lands at one certain point just doesn't make a lot of sense. It's so unlikely that one specific point and not any infinitesimal distance to the right or the left of it. That just doesn't make sense. But you can define a reasonable probability that it lands between this point and this point, just like you can define a reasonable probability it lands between this point and this point, right? And it is more probable to land here, but we can't really define some probability there. So here is how we work this out in quantum mechanics. Instead of that probability expression, we say that the norm squared of the coefficient, right, is equal to the probability density of Q. Right? And so I'm going to graph this, and I'll show you sort of what this means. So if I've got a graph that looks something like this, right? And so I've got here, this is our x-axis, right? And we'll deal with position for right now, okay? So this is the probability density of landing at that position. So if I have a point right here, right? right? I can't really define a probability at that one point, right? But I can define a probability between, right here, call this x, and then this point, which is x plus dx. Okay? And this probability, I'll call it, it's our infinitesimal probability, because in an infinitesimal range, right, the probability would be infinitesimal. This dp is equal to rho of x times the little width of this rectangle, right, times dx, right? And so the probability, right, or I'll write this out sort of in this way. The probability that the particle lands between x and x plus dx, right, is equal to the probability density times dx, right? This is probability per unit length. That's why it's sort of a density, right? Because it's probability. You can also rearrange this to be rho of x is the probability of x of between x and x plus dx over that distance, the probability per unit length, right? That is what probability density is. And if we also notice what the units of this are, the probability density has the units, or I'll actually say the not units but dimensions. That's green. Dimensions has the dimensions of, I'll redo this because, so if you remember, probability has no dimensions, right? Probability is a ratio, so it's dimensionless. The dimensions of probability density is 1 over length, right? Because 1, that there's no dimensions for probability, right? And so then we can also see that the coefficient cx has dimensions, right? The dimensions of cx is equal to 1 divided by the square root of length, which is actually going to be a bit more important a little bit later in this course, but we'll get to that when we get to it. So hopefully this makes sense, and I'm going to write down some new expressions that we can get from here. So if we wanted to know the probability, say, between this point A and this point B, we would just add up all the little, right, because the area of this rectangle is the probability, right, because, since this dp, it's this distance times the probability density, it's the area of this rectangle. Then we'd have to add the probability here, 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 infinitely add up all the infinite continuous amount of infinitesimal probabilities, right? That sounds like the work for an integral, right? So we can actually sort of see graphically here that it would make sense just by adding up all of these infinitesimal dp's. The probability that you land somewhere between a and b, right, is the integral from a to b, right? We're summing up from a to b of all these infinitesimal probabilities, right? But what is dp? dp is just rho of x dx, right? So the integral from a to b of rho of x, right? But I'm actually going to rewrite that one more way. Actually, I'll write it here. I'll write rho of x. This is rho of x dx, right? But this is also the integral from a to b of c sub x norm squared dx, right? This also makes sense. C sub x norm squared has units, right? C sub x is 1 over root length, so this is 1 over length times length gives you probability, which is dimensionless, right? And so I may actually rewrite this a little bit too, just so you can sort of see a little bit more of the idea. Because a and b in this case, and you'll see why I'm doing this, this is between some point x1 and some other point x2. The probability that you land between x1 and x2 is the integral from x1 to x2, right? The reason I'm writing it like that is because we can extend this to any, right? Because there may be other continuous quantities, and we'll see sort of what quantities are continuous. We'll be able to develop this a little bit more throughout this course and throughout this section. So, but landing between, or the probability that the particle has some value of q between q1 and q2 is the integral from q1 to q2. Right, this is just generalizing it into q instead of just position, right? Any continuous quantity from q1 to q2 of rho of q dq, right? Which is from q1 to q2, right? This is just using this identity right up here of c sub q norm squared dq. Right? So the c sub q norm squared does have a significance. It's the probability density. It just wouldn't make sense because there's a continuous number of possibilities. It would not make sense to call that the probability. Okay, so the last thing that I wanted to talk about in this video is we have this idea of normalization, right? That we've talked about in the previous section, and we actually have an analog for that in this continuous case, right? Notice, right, what is the probability that the particle has the value of the observable between negative infinity and infinity? Well, it's got to have some value of that observable. This has got to be equal to 1, right? This is the integral from negative infinity to infinity of c sub q norm squared dq, and I'm going to erase this bottom part right here, and this is equal to, well, it's got to equal 1, right? And this is our normalization condition. And this works for position too, c sub x norm squared dx, right? The integral from negative infinity to infinity. All this is saying, this is just saying, if I'm summing the probability density, if I'm taking the probability over all the possible values from negative infinity to infinity, all the possible values of q, I've got to get 1 at some point, right? I've got to get 1 just because it's got to have some value between negative infinity to infinity. From negative infinity to infinity. The probability of having some value there is 1. And this integral definition actually works as well. For another reason, I'm going to erase this. Hopefully you have this all down. This is the last thing. When we're summing up, right, from negative infinity to infinity, you may ask, well, would we need to change that if, say, the particle can only be between like x equals, negative 5 and 5, right? So if I've got negative 5 and 5 right here, and here's 0, right? Well, if the particle can only be between negative 5 and 5, and we'll actually see in section 4, we're going to derive an equation involving this kind of situation, right? Its probability may look something like this, right? And if I'm not probability, this would be its probability density of x, given this is the x-axis. But this would work for any observable, right? This could be momentum, anything, right? But say its position can be somewhere between negative 5 and 5, or alternatively, its momentum can be between negative 5 and 5, and this would be rho of p, right? Well, if we're summing up the probabilities from negative infinity to infinity, right? Well, it's 0 over here, right? So there's no area here, and all the areas here. So the integral from negative infinity to infinity would really just be adding up the area from negative 5 to 5, right? So this negative infinity to infinity thing actually lets us account for, in general, all possible values, right? And so then it would just be, you'd only be adding up from negative 5 to 5 because all the rest of it would be 0. That doesn't make sense, just sort of accept this value, but this is just sort of to explain why negative infinity to infinity works for all cases, even if there's, a range of the only possible values that x can be, right? Then the integral from negative infinity to infinity just becomes the integral from negative 5 to 5, but the equation from negative infinity to infinity is still valid, right? Because if you do it, you're just adding up, right? So hopefully that makes sense. I could prove this more rigorously mathematically, but I don't think anybody really wants that. So yeah, that's it for this video, and I'll see you in the next video.